Hello, everyone. I'm coming to you live from my room. I know it's not live for you, but it's live for me, so give me a break. I'm sorry. Today is a crash course at Suffolk County Community College by yours truly, Professor Gardner. Now, you could just call me Corey because, I may or may not be a real professor, but that's besides the point. Today, we're going to be going over behavior between regular and derivative graphs. That can go for either the first derivative or the second derivative. Don't worry, we'll get into that. Looking back at what we were learning last week about what derivatives would tell us about the shape of a graph, this lesson is going to kind of build on that concept because you already know that when you looked at a function f of x, whether it was increasing or decreasing, you knew that at that critical point, you knew that if it was greater than zero, it would be increasing. If it was less than zero, it would be decreasing. And of course, if the derivative was equal to zero, you know that it would be a constant because of that fact. So you see our little Winnie the Pooh appear, he doesn't really like decreasing. He thinks that's a blatant term, so we're going to use the term de-increasing just for this joke because, humor. But more so on the idea of the first derivative graph. We also learned about the second derivative of a function. You knew that based off of the second derivative that if it was greater than zero, it would be concave up, and if it was less than zero, it was concave down. I agree with our friend Will Ferrell here. You might think he's Elf, but no, it's just Will Ferrell in a Christmas costume. Concavity, I wouldn't say it's fun to say. Oh, but it's really fun to do. I'll agree on that front. But it's the holiday season. Santa Claus is coming by. I'm going to be looking back at this and thinking, man, I was really unfunny, but if I get a few pity laughs out of this, I say that's a win. But moving on, we have an example here, and we're basically going to take the first and second derivative and figure out whether it's increasing or decreasing, and where the critical points are that would tell us where to break it up if it was increasing or decreasing. I will now have Professor Gardner in real life pause the video so that you can do this. I'll give you a minute. Go. That worked out nicely. A minute for you was a second for me. So now, looking at the fact, I'm going to start going over it. So first, we're going to start by taking the first derivative of this function. So doing a basic power rule, I'll rewrite it because I know the carets don't exactly do a great job. So we have x cubed plus 12x squared plus 36x. Knowing that, we're going to take the first derivative, so f prime x equals 3x squared plus 24x plus 36. Okay, so knowing that's the first derivative, we're going to find out whether the function is increasing or decreasing. But first to do that, we have to set this function equal to 0. So we're going to do 3x squared plus 24x plus 36, set it equal to 0. So we're basically just going to find the zeros. We could take a 3 out, do an x squared plus 8x plus 12. That'll give us, if we put on the 3 here, x plus 6, x plus 2. So we know that x equals 0 at x equals negative 6 and x equals negative 2. So knowing that information, we now have our critical points that we're going to put on our number line. So we're just going to make one big number line. We'll have negative 6 and negative 2. So now from here, we're going to use a value that is less than 6, a number that's between negative 6 and negative 2, and a number that is greater than negative 2. So here, I guess for negative 6, we'll just plug in negative 7 into the equation. So we have negative 7 plus 6, which will give you negative 1. We'll have that 3 there. Then negative 7 plus 2, that'll give us a negative 5. So we'll have negative 1 times negative 5, which is positive 5, times 3, which is 15. That'll give us a positive. Then we'll do a number between negative 6 and negative 2. We'll do negative 4. So negative 4 plus 6 is 2, times negative 4 plus 2 is negative 2. That'll give you negative 4 times 3, which is negative 12, which is negative. Okay, so now we're going to choose a number that's greater than negative 2. We're just going to do 0 because it's easier. Okay, so we have 3 times 6 times 2. We know that's positive. So now we know that increasing wise, we know that f of x is increasing at the interval negative infinity to negative 6, then we know it'll stop in the middle there. It'll go from -2 to infinity. And we know that it's decreasing at from -6 to -2 because of that fact. Now, in order to find whether it's concave up or down, we now need to take the second derivative. So we had the first derivative over here, so just do a quick power rule. We'll find that the second derivative is equal to 6x plus 24. So now, same thing as before, set it equal to 0. So 6x plus 24 equals 0. Subtract the 24 from both sides. We are back after a lot of headache, to say the least. That was very annoying, to say the least. Now, we were trying to figure out if it was concave up or down. So we're going to set this equation, which is the second derivative, equal to 0. We're going to subtract 24 from both sides. We're going to get 6x equals -24. Divide by 6, you get x equals -4. So we're going to make another line at -4. So now we plug something less than -4 and greater than -4 into the equation, whether to see it's concave up or concave down. So let's do -5. -5 times 6, so -30, plus 24. That'll give you a negative number. So it's concave down. Okay. And then we'll do a number greater than -4. We're going to do 0 again because that's easier. And we get a positive. So we know that from -infinity to -4, it's concave down. And we know from -4 to positive infinity, we're concave up. Okay, that's it on this problem. Let's move on. Now we're moving to the new stuff. This is what we're going to be talking about today. We know that in certain behaviors, in certain graphs, we'll be able to tell the differences or almost like predict in a way for the other functions. So when looking at the regular function of f of x, you can realize that when f of x is increasing on the graph, it'll be the same as f prime x, so the first derivative of x being positive above the x-axis. And so it's the exact opposite when f of x is decreasing. You know that the f prime x, the first derivative, is negative. It'll be below the x-axis. As for when f of x is concave up, you know that double prime x, which is now the second derivative, is also positive. And if it's concave down, you know that f double prime x is negative. We're about to look at some examples that'll help visually understand it. On the next slide, it says, for example, given the following functions, we're able to graph it and be able to tell where the first derivative and the second derivative is positive or negative. So let's start off by looking at the first equation. We have x to the fourth plus 2x squared plus 12x. Let me rewrite it here because it can be a little tough. Oh, we don't want to go that far. It can be a little tough to see. So we have x to the fourth plus 2x squared plus 12x. So we're not going to be solving algebraically. Instead, we're going to be using our very own applet that we use a lot. We're just going to be using Desmos. I figure that's the best way to visually show the difference in these derivative graphs. So we have the regular function f of x, which is x to the fourth, plus 2x squared, plus 12x. Oh, that's not it. Okay, so we're able to see that this is just the first derivative. It has the critical points at -2 comma 0 and that's not -0, it's just 0 comma 0. Okay, so here the best way we're gonna be able to figure this out, just take the first derivative. So we're just gonna do a quick power rule. We get 4x cubed plus 4x plus 12. Okay, so we're gonna take away this one for now, and we're just gonna look at this one. All right. If you're just looking at the first derivative graph of this, you can see that it's negative for a while until it reaches this point, and ironically enough, that point is 0. 0 comma 12. So no, if we go back to our regular graph now, we can tell that on this little range from -2 to 0, you can see that at 0 it begins increasing again. And lo and behold, if we go back to a rule that we went before, when you know that the interval starts increasing again, you know that this value, the first derivative, will become positive. We're now going to look towards the second derivative of this equation in order to find where its being positive or negative, which we'll find by basically showing the concavity of the original function. So here I have written down 12x plus 4. That is our second derivative of the equation. So let's just get rid of these. So now right here, it's just shown a basic parabola at the center of 0, 4. That's our vertex. Now, if we look back at our original function, which is regular f of x, you can see that the concavity, since it's also a parabola, is always concave up, which is the exact reason why, if you take it off again, this entire thing is above 0. It's never going to be negative, above the y-axis, which in this case will show that it's always positive. Okay, now looking back at our examples here, we have another one that'll help us even more in order to better understand this problem. So we have x cubed minus 7x squared plus 4x plus 12. This is definitely a longer one, but that doesn't mean it's any less easier because yet again, we're just literally going to go towards our Desmos graph. So we're going to get rid of what we have here. Okay, bear with me. So instead of that, we are now going to copy in. All right, so we're on Desmos now, and we have our function all graphed ready for us. We have x cubed minus 7x squared plus 4x plus 12. So we could see here that we have 3 critical points on this graph. It'll be -1, 2, and 6. So those are our 3 critical points shown on the graph. Now looking on the graph, we know that we need to find when f of x is increasing in order for f prime x to be positive. So if we look at this, we'll be able to see, let's just work on our function for now. Let's just do from -1 to 6. We know that from -1 to about maybe 0.25 about, we'll find that it's positive. But then from that point all the way down to about, let's see, that's about maybe 4.5, it'll be negative. But then if we go all the way back up to 6, we'll find it to be positive again. So if we take a look at our first derivative, 3x squared minus 14x plus 4, we should find that at the exact same intervals, we'll find that it's positive all the way up until that 0.25 point, negative all the way up until the 4.5 I had mentioned before, and then it goes back to being positive. This all takes place in the interval that we had previously set because of the critical points. Now, if we look back at the original function, we'll be able to tell the concavity of this function and whether that'll mean in the same interval as before, whether f double prime x is positive or negative. So here let's just graph our function. The second derivative will be 6x minus 14. Okay? So now we'll be able to tell from here, these 2 points interconnect and these 2 points interconnect. Now, if we look back at the original function, we'll be able to tell the concavity of this function and whether that'll mean in the same interval as before, whether f double prime x is positive or negative. So here let's just graph our function. The second derivative will be 6x minus 14. Okay? So now we'll be able to tell from here, these 2 points interconnect and these 2 points interconnect. When looking at these 2 points, they're very important in understanding whether or not it works. So now that we look at this, from the same points we had set before, -1 to now at that point where they interconnect, we'll be able to clearly see that at 2.111, from -1 to 2.111, it is concave down, which means this value is negative, up until the point where over here at that same exact point, it'll start going concave up, which will then lend itself to become positive in this direction. So that'll further prove the statement that the concavity of the original function accounts for whether the second derivative is positive or negative in that given interval. Now we're going to move on to relationships that the first derivative graph represents. So even though we've already been given the first and second derivatives from the original function, sometimes you'll be given the graph of the first derivative and you're supposed to find stuff from the original function and the second derivative function. So now that you know you can use some of the same things you learned before in the normal function in order to find it. So like it says here, if f prime x is positive, then you know that the original function f is increasing, and if it's negative, then you know that the original function is decreasing, as shown before. But now, if you see that f prime x is increasing, you will know that the second derivative is positive, and if f prime x is decreasing, then you know that the second derivative is negative. So it's basically what the original function does for the first derivative, but except it's almost just applied over different ways. So now we're going to look at two more examples that'll help us demonstrate that idea. So let's look at these examples. First up, we have, let's get this going. Okay, so we have 3x squared minus 6. Yeah, you might be thinking to yourself, that's a pretty easy equation. Why would we have to do something like that? This, in fact, equation given to us is none other than the normal, or I'm sorry, the first derivative here. So see it says f prime x. So we know that f prime x is equal to that. So we're going to go back on our best friend Desmos in order to find how the original function and the second derivative function will be when we see it graphed. So here on Desmos, we have our original function, or I'm sorry, our derivative function, 3x squared minus 6. If we go back to what we did before, we know that whenever f prime x is positive, then we know that the original function f is increasing. So we see the critical points here, negative 1.414 and positive 1.414. We know from negative infinity to the negative and from the positive to infinity, we know that the function f is going to be increasing, but in between these, we know that the function f, the original, is going to be decreasing. And we'll be able to see this when we enter in our original function. So the original function that we have is x cubed minus 6x. You see it because 3x squared minus 6. So let's take off our original. So in the values, we're supposed to have it, we know that the function is going to be increasing for a certain amount and then decreasing for a certain amount. But they're all in the exact same interval, negative 1.414. So we knew that up until this point it would be increasing, then in this tiny little interval here, in this little interval, it would be decreasing, which is shown here from the top of this to the bottom of this, where it starts increasing again. But you can see it's the exact same points shown in the derivative. If you see here, the zeros doesn't want to work. Negative 1.414 and positive. So that demonstrates the first law of when you know that if it's positive, it's increasing, negative, it's decreasing. It's basically the opposite of before. But now we're going to go over the second derivative. So the second derivative is dependent on when f prime x is increasing or decreasing. So let's take the next derivative of this. So the derivative of 3x squared minus 6 is just 6x. That's it. Just a line. But we know from here that if it's decreasing, then you know that the second derivative is going to be negative. And then when it starts increasing, then you know it's going to be positive. And you can directly see here that once it starts increasing at the 0, it starts becoming positive again. It goes from this point all the way up. At 0, 0, it changes into a positive number. So that demonstrates the other example of it, where if f prime x is increasing or decreasing, that shows whether it's positive or negative, distinctly shown here. So now looking back to our other example, we have 12x squared plus 16x, which can be seen, I wrote it out for you already, and we can already tell that it's already giving us, this is another derivative function. It's not the original function, but the derivative. So now, if we go back on Desmos, bear with me, we have the original function, which is 12x squared plus 16x. You could see that it's a derivative here as well. So now, using this information, we now graphed the original function, which was given to us as 4x cubed plus 8x squared plus 2. So as you can see, when we graph the original function, we can see that the original function, which is given to us here, is increasing up until this point, which means up until this point, this is the derivative, it's positive all the way up to here, which is the exact same point that it stops being positive, or increasing, I'm sorry. So now that we can tell that, we can also tell that when the function over here starts decreasing, it's also negative here. But then up here, since it's a parabola, it starts increasing again, and our value in the first derivative also becomes positive again. So that demonstrates the idea that given the first derivative of a graph, you can tell whether it's positive, increasing or decreasing based on the positivity or the negativity of said graph of the first derivative. Onto our last little snippet. You're usually not given, at least in my experience, the second derivative and have to find the first and the second. But if you have to, you all you have to do is kind of cycle back and use the other stuff and kind of reverse it. If f double prime x is greater than 0, you know that f prime x is increasing. Same for when it's less than 0, it's decreasing. And then you'll be able to figure out if the original function is concave up or down based off of the positivity or the negativity as well. So we are now on to our final example of this lesson. We're going to, given the function, take the first and the second derivative and use the second derivative graphically to determine whether f of x is concave up or down and whether f prime x is increasing or decreasing. So this is going to kind of incorporate everything we've done. I'll give you guys a minute to take the first and second derivative down, and then I'll go over it graphically. Looking at the second derivative on the graph, you can tell that there are two critical points, negative 1.816 and negative 0.184. Now, judging based on this, we can tell that the second derivative is always positive. That'll tell us that the original function is concave up. Okay. And so it goes for the opposite. When it's concave down, it's going to be negative. So we could show here that using the original function graphically, we can see that all the way down here, at this point, it is in fact concave up. And that goes perfectly along with this value being positive. So we could tell because concave up would give us the exact same point. Now here, we can tell, since this is obviously a very long thing, that this also looks like a parabola that will also keep increasing. But you can see here that it's negative for a little bit, meaning for a little bit of time, it goes concave down. Now, looking at the second derivative of the function, we'll be able to tell whether it's increasing or decreasing based on whether it's positive or negative. So positive is increasing, negative is decreasing. So at these given values, we'll be able to determine inside the interval where it's increasing and where it's decreasing. So let's look at it. We can tell up until this point, it's increasing, which is the exact same point where it goes negative, and it starts decreasing again. And then at the moment where it starts increasing again, it is positive. So that definitely sounded like a lot, but it all stems back to the simple rules that what we went over before, which was if it's greater than 0, we know that it's concave up for the original function and increasing for the first derivative, and if it's less than 0, we know that it's concave down on the original, and the first derivative is decreasing. That is it. You have made it. Congratulations. That's it for today's lesson. You have now completed Professor Gardner's crash course in behaviors between derivative graphs. As you can see, you have earned these very good memes. We have Tom over here saying when someone says they are good in maths, you get challenged by derivatives, and we haven't even gotten to integrals yet. So that's going to be fun. And, I love the old tangent joke because, this may not have been about sine and cosine trigonometry, but calculus puns are completely derivative. I think that's pretty funny. Well, thank you for your time, and let's have fun watching everybody else's, shall we?